Hi, I'm Jason.
And I'm Harry.
And we're going to tell you about a
loophole-free
loophole-free Bell
Bell
test. Pretty cool, right? Yeah. In order to do that, we're going to ask you to take a trip back in time with us to learn about quantum theory and the birth of it and some of the different disagreements that arose from it. So put on your time travel suit and come along with us.
And after that, I'm going to explain the ideas behind Bell's test, qualitatively and somewhat quantitatively with examples. And we'll leave you off with a rap about the loophole-free Bell test.
And it's really cool. We wrote it ourselves, and Harry's on the instrumentals.
Not the test, but the instrumentals for the song.
The instrumentals for the song, not the test. But although Harry's pretty smart, he could come up with it. Anyway, but we hope you guys enjoy our video. Thanks, and enjoy.
Enjoy.
The purpose of this video is to explore the experimental results of a loophole-free Bell test which was conducted by physicists at Delft University of Technology in 2015. Therefore, it is vital to provide the context surrounding the experiment, and thus we must begin by asking and then answering the question, what is quantum theory? To do this, let's go back in time to 1927, where a young Werner Heisenberg presented a paper to his mentor Niels Bohr on his idea of the uncertainty principle. After reading the paper, Bohr suggested that Heisenberg withdraw it due to its narrowness, but Heisenberg refused. As fate would have it, their disagreements and agreements led to the birth of the Copenhagen interpretation. Heisenberg's uncertainty principle, Bohr's complementarity principle, and Born's statistical interpretation of the probabilities of the wave function. Of course, not everyone agreed with the idea of randomness. The Copenhagen interpretation was an explanation as to the physical meaning of quantum theory. Summed up, the principle stated that the collapsed wave function and its resulting measurement were the only reality in physics. Of course, not everyone agreed with the Copenhagen interpretation. Notable physicists such as Max Planck, Louis de Broglie, Schrödinger, and Albert Einstein disagreed with the Copenhagen interpretation. It was in 1935 when Schrödinger presented a paper titled The Present Situation of Quantum Theory. The paper contained a thought experiment in which you take a living cat and radioactive material which has a 50% chance of decaying. You place both inside a box and close the lid. Assuming that quantum theory was correct, the cat was in a superposition state in which it was simultaneously alive and dead, and therefore we cannot know the state of the cat until we open the box. Schrödinger argued that intuition tells us that the cat is either alive or dead, and the act of taking a measurement by opening the box does not change that. In 1935, Einstein, Podolsky, and Rosen presented their paper titled, Can a Quantum Mechanical Description of Physical Reality be Considered Complete? In order to support their argument, the authors used a method of contradiction by assuming that quantum entanglement was true. They then supposed a situation where a source emitted an entangled pair, where an electron moved to the right towards Alice and her detector, while the positron moved to the left towards Bob and his detector. The idea was that the electron reached Alice a split second before the positron reached Bob. Therefore, during that split second, the positron would have to know what spin orientation to have. This meant that the information had to travel faster than the speed of light, which of course contradicted the theory of relativity. Einstein, Podolsky, and Rosen therefore believed that there were hidden variables at work and concluded that quantum theory was incomplete.
The Einstein-Podolsky-Rosen paradox implicitly assumes the idea of locality. Locality means that one thing affects another thing through intermediate steps of cause and effect. But John Bell in 1964 showed that this is not the case with quantum mechanics. Quantum mechanics is fundamentally non-local. My assistants Otto and Walter will assist me with demonstrating the non-local effects of Bell's test in a qualitative way. First, Otto and Walter find a twin light source, a source of light such that both photons have the same spin. They can be spin up or spin down. They start with both of their Stern-Gerlach apparatuses are oriented in the z direction. Notice the photon spin is indeterminate, but Otto and Walter still seem to get the same spin. Let's fast forward a couple frames. Now we know when their Stern-Gerlach apparatuses are on the same axis, they get the same values. What happens when one of them has a value of 30 degrees relative to the other one? They can see that there are differences in the signals that Otto and Walter are receiving. There's a 25% difference. It happens when we tilt the other Stern-Gerlach apparatus by 30 degrees, leaving the remaining apparatus in the z direction. We get the same result. What happens with both apparatuses tilted at 30 degrees, each in opposite directions? Where things start to get strange, you would expect a maximum of 50% difference between the two measured values. In actuality, there's a 75% difference. What's going on here? This demonstrates the non-locality of quantum mechanics. The quantum strangeness of non-locality was found because it violates Bell's theorem. A simple form of Bell's theorem states that for a local theory and given any properties A, B, and C, the number of outcomes satisfying A and not B, and the number of outcomes satisfying B and not C is greater than or equal to the number of outcomes satisfying A and not C. This can be seen to be true by noting that if something satisfies A and not C, it satisfies B or it doesn't. If it does satisfy B, it can be counted as satisfying B and not C, and if it doesn't satisfy B, it can be counted as satisfying A and not B. Now let's see what happens when we try to apply this to quantum mechanics. Let's say we are looking for a spin-up particle at 0 degrees with a Stern-Gerlach apparatus and its pair at 45 degrees. We're also looking for a spin-up particle at 45 degrees and spin down at 90 degrees. This would mean A is a spin-up at 0 degrees, B equals spin up at 45 degrees, and C equals spin up at 90 degrees. Plugging this into Bell's inequality, we get a violation. Quantum mechanics is shown to be non-local. Now that we've laid the foundation of Bell, we have a very special story to tell. So some don't accept what Bell has to say. They think loopholes might not point in his way. One is communication and the other is detection. Physicists from the Netherlands provided a correction. Detection and perfection should go hand in hand. You can fake quantum correlation without a synchronous time span. Communication is one factor. Detector can act as another's benefactor. If you can separate them by a big enough distance, they can't communicate through any physical assistance. There's also something that I forgot to tell. They use an event-ready test proposed by Bell. It started with a diamond with a nitrogen hole, optically pumping sets it on a roll. A closed cycle cryostat at T equals K is utilized to keep any thermal noise at bay. M sub S of 0 is defined as 1, negative 1 or plus 1 is 0 just for fun. The spatial separation gives us only 4.3 microseconds to compare. After random basis, there are 90 nanoseconds to spare. Two photons travel down fiber optic cables. It's to make sure they don't share any information tables. They go through a beam splitter are detected. The experiment's complete. The only thing left to do is repeat. 45 times they compared, but there's one loophole of which they were scared. Detectives could react to previous trials. The sightings respond with any denials. A p-value of 0.039. Well, I know it's still pretty fine. You asked about Bell test and now you know, so you should stay tuned for the next show.